And the first speaker is Tushar Menon from University of Oxford.
Thanks, Château. Thanks for coming, everyone. I sort of feel obliged to also thank the organizers for this fantastic event, the wonderful accommodation, the great liquid meals. So first of all, if you were expecting more jokes, you're going to be disappointed. I just used it all up in the title. So I'm going to be talking about, oddly, space-time and quantum gravity, something we haven't heard a great deal about, I think, this week. I'm going to be, in a sense, piggybacking on a lot of what Eleanor and Al said in their keynote talks, but not having a permanent job myself. I'm at a lower pay grade, so I'm talking about something much, much simpler, which is still largely motivated by similar things to what Eleanor, for example, is motivated by. And as just a quick sort of recap of what the sort of space-time functionalism project is, it's not intended to be a sort of once and for all conceptual analysis of the concept of space-time, but rather it's kind of identifying what concepts make up this cluster concept that we talk about as being space-time. So, motivated by wanting to recover some notion of empirical coherence, which was the sort of thing that Eleanor was talking about as well. I'll talk a bit more about exactly what this means, but I suspect most people in this room know what I mean when I say empirical coherence. I want to capture an aspect of space-time structure that I think is quite important and actually just requires a lot less sort of fancy machinery than some of the things that we've heard about. So the structure of the talk, it's basically 3 sections with an appendix that I may or may not get to because it's sort of important, but depending on time. So the idea is I'm basically going to speak a little bit about what motivates my view. I'm going to then talk about the view, and then since Nick is in the audience, I'm going to talk about, I think, the same paper that Eleanor made reference to. But I'm going to come to just a slightly different, not inconsistent conclusion. And so that's that. So let's get started. Now, the starting point is pointer readings, dial readings. Those are the sorts of things that give us evidential support for our best theories of physics or anything really. And so, if we expect to tell a coherent story about why we might have a good theory of physics, the obvious thing to do is to go out and test it. And the way that we test it is by sort of looking at what corresponds to the sorts of things that we think of as being real in our theory, looking at the things that exist in space-time that somehow emerge or not from our theory. But of course, as we've seen in a bunch of talks so far, and as is sort of, as Kareem put it, one of the 2 dogmas of quantum gravity. Sorry to spoil the surprise in the title of that sure to be forthcoming paper. Sorry? I do what I can. Maybe by the end of the talk, we'll have a second. So the idea is, look, if we think of GR and if we think of quantum field theory separately, we actually don't really have a problem of space-time. They both independently are perfectly well-defined theories for arbitrarily short lengths, sort of modulo concerns about renormalization for certain theories in QFT, but the kinds of theories that we think of as being sort of quite robust theories of quite robust examples of quantum field theories are renormalizable, so everything's okay. The problem comes in because basically the metric field in GR appears to play a dual role, and if you were a particle physicist and sort of inclined to believe that gravity was a force, that would be the kind of thing you'd want to quantize, and the thing you'd end up quantizing would be some aspect of, well, it would be something that had some kind of metric properties. And of course, one of the things that the metric does is it allows us to account for smooth particle trajectories, and if the metric is quantized and subject to quantum fluctuations, then we don't have this anymore, and it then looks like we don't have fundamental local beables. But of course, we don't need fundamental local beables. We just need local beables. And as we've seen, there are various stories that you can tell about how that might happen. So I'm just going to, this is what I call the easy problem of quantum spacetime, with sort of credit and royalties due to Dave Chalmers, obviously, for that. And there are two reasons I call it the easy problem of quantum spacetime. One is it is easier than the hard problem, which I'm going to mention but then just drop. And the other is sort of continuing with where the nomenclature came from. Chalmers has this idea that you can sort of give functional explanations and functional answers to the easy problems of consciousness. And I'm proposing a functional answer to the easy problem of quantum spacetime. And the motivation for sort of addressing this comes from a quote from Geroch's famous 1972 paper on Einstein algebras, where he says the metric is the primary tool for isolating individual events. Notice he says the primary tool, he doesn't say it's the only tool, but it's this event isolation thing, this event isolation structure that I'm interested in recovering, because it's when we do experiments, when we do science, when we do physics, it's not just space-time distances and angles and sort of stuff about motion and inertia that we measure. At a much sort of more basic level, we measure whether or not two things are located at the same point in space-time, and that seems like something that we might want to recover, even when we lose sort of some of the other fancier things when we deal with emergent space-time. So if there's an easy problem, there's a hard problem, and the hard problem of quantum space-time is basically the problem of quantum gravity. I've sort of formulated it in terms of a hard problem for a quantum field theory of gravity, but if for various reasons you believe that the final theory, quantum theory of gravity, is not going to be a quantum field theory, replace renormalizable picture with some new theory, whatever. Basically, I'm not interested in the hard problem. I'm interested in the easy problem, which is this. If the space-time metric is to be quantized, as I said earlier, how do we consistently individuate space-time events if, as Geroch says, the metric is the primary tool for individuating such events? And of course, the answer is we look for a secondary tool. So I'm going to frame all of this as a discussion about based on Nick and Chris's 2013 studies paper, where they look at various theories of quantum gravity. And they say something, I'm paraphrasing, something along the lines of, look, we have a fairly good intuitive idea of what constitutes space-time and sort of theories like special relativity and the like. How many of these characteristics can we sort of take away and still retain this notion of spatiotemporality as we go through various theories of quantum gravity? And they show that, you can take away a lot and still not fall prey to the charge of empirical incoherence, which is the charge that your theory, the truth of your theory might undermine your reasons for believing that it is true. So let's focus on four roles that space-time, that the objects that you might think of as being associated with space-time might play. There's this event individuation thing, which I'm going to talk about today. There's causal structure, which is basically angles in space-time, and those are invariant under conformal transformations. There's, of course, lengths and distances, which is a metrical notion. And then, depending on whom you ask, but I think it's a fairly safe thing to say, a potential for the gravitational field. Obviously not the gravitational field itself, but just the potential. So I claim that once you lose event individuation, then you've definitely lost empirical coherence, because now you no longer have a way of even vaguely identifying local beables. But of course, event individuation only needs to happen to the extent that you can empirically access two different events. So in order to save empirical coherence, we don't need event individuation, we don't need this sort of distinct points on a manifold idea to go sort of, as it were, all the way down. You just need to be able to individuate events at the level to which you can probe space-time. So as I said, a space-time event in the way that we use it in our theories of physics is an idealization. Obviously we never measure space-time events, but we also never measure point particles or things localized to extensionless space-time events. But that doesn't mean we don't sort of brazenly express our results in terms of coordinates that do, in fact, name these events. So what I want to do is, instead of talking about sort of the manifold itself, I'm going to talk about something that I call an emergent manifold. And I'm willing to change this word supervene depending on, based on conversations that I might have with sort of people like Al and metaphysicians who take this sort of, who think about these things a lot more deeply than I do. But I use supervene just because it's a relation, it's a two-place relation that allows me to, that allows for multiple realizability, and that's really the thing that I'm after over here. So call something an emergent multiverse. Talk about a Freudian slip there. Call something. Hi, David. Call something an emergent manifold if it supervenes on exact manifold structure, which is to say, I've got some mathematical description of a manifold. I've got some mathematical description of what I think of as being space-time. I model that as being a manifold. But it might be the case that there's something else that instantiates that manifold structure, which itself can be thought of as an approximation of exact manifold structure. And this allows me to still use the language of coordinates and coordinate systems with no real problem. So as I said, we have this problem with using the metric to individuate events. And so if individuation structure is not fundamental, what kind of structure can this emerge from? And this is sort of the crux of the talk. I suggest that it can emerge from the behavior of the dynamical fields in your theory. And this is sort of very much in line with Harvey Brown and Oliver Pooley's dynamical approach to relativity. Yeah, this is just something I mentioned earlier. I don't know why I have that in this slide. So before I get onto the actual sort of details of the program, I want to ask, why would Geroch say that the metric acts as an event individuating field, given that in relativistic theories on a Lorentzian metric, the sort of the algebraic function that the metric plays of assigning, of taking two elements in the set and mapping it to a real number, on its own will not individuate events on a very natural way of thinking about individuating events as sort of two events being distinct if the distance between them is non-zero, because as we know, the signature of the metric allows distinct, what we think of as sort of intuitively distinct events to still be mapped to a zero distance. Yeah, that's what I just said. So I contend that it's actually topological considerations that specify event individuation structure, and in some cases the metric respects this event individuation structure. In other cases, the metric, or the algebraic function of the metric, sort of doesn't, but we still use, and at times like that, we rely on this topological considerations. And when I say topological considerations, I mean specifically the Hausdorff condition, which says that if I've got any two points in a topological space, then I can find two open sets, well, an open set that contains each of them such that those open sets are disjoint. And that's really intuitively the kind of thing that we want. We want to say, okay, I don't really want to find sort of every point on the manifold. I just want to find sort of a region of the manifold to a sufficient level of description such that I can distinguish between events that sit in the equivalent of open sets. So if we can derive the structure from the dynamics of the fields, and the fields may be classical, the fields may be quantum, then maybe we don't fully solve the easy problem. That might be a bit much, but we're certainly a good way along the path to solving the easy problem. So that's the sort of that's the basic setup. Now I'm gonna go through the details of the construction. It's actually quite simple, and I'm going to do it in terms of classical linear field theory. If we have time in the appendix, I'll talk a little bit about why the same thing can be sort of very easily generalized to quantum mechanics and quantum field theory. But my presentation is based on this coordinate-based approach to geometry that sort of traces its way back to Klein, it's sort of explicit in the work of someone like Harvey Brown. My current presentation is sort of lifted almost exclusively from David Wallace's recent paper on coordinate systems. So here we go. Now, I had trouble when I first learned about manifolds and differential geometry, and I suspect a lot of other people did. Because there's a moment where things suddenly appear to stop being constructive. So you can say, look, I've got a set, however I've got a set. I've just got a bunch of points. I've got a bag of set point powder. And I can give it topological structure. I can do it sort of by hand. You can specify what the open sets are and which open sets satisfy certain conditions. And I can build a topological space out of that. But it seems like I stumble when I want to define something like differentiability, just manifold structure, smooth manifold structure. Because it seems then that I'm appealing to certain properties of the coordinate systems that I'm using. Specifically, that if I've got two charts on the manifold, then the transition maps between them have to be, so if I want a smooth manifold, then the transition maps have to be smooth, which is to say they have to be infinitely differentiable. And in order to define that differentiation, I'm actually really using metric structure in my coordinate system. And so that seems like a bit of a disquiet. And really what the motivation behind this way of thinking about geometry is to say, yeah, that's a completely legitimate way to think about geometry. In fact, why use that for just topological manifolds and smooth manifolds? Why not just use it for any kind of geometrical space that you might want to construct? And so that's the approach that I'm going to be considering today. So now, I've got my space. I think I've called it M. Yeah. So I've got my space M, my set, and I want to structure it as a topological manifold or a manifold or a smooth manifold or whatever. The way that I can do that is by specifying a bunch of maps from the set M into the real numbers. Well, into n-dimensional Euclidean space actually. And then exactly the same ways I define the smooth manifold, privilege certain transition functions, privilege certain ways of coordinatizing this set. So a topological manifold is defined by certain automorphisms on the, so I've used Rn to represent the Euclidean space, which is a bit of an abuse of notation, but I think only Casey is really going to have a problem with that. So as I said, we now have a way of characterizing M as, for example, a topological manifold without having to define intrinsic metric structure to define the open ball topology or the standard topology. So now let's just generalize this idea to define structured spaces that don't just preserve some kind of geometric structure. They might preserve the form of some kind of dynamically or perhaps even kinematically significant equation. And this is the space in which Harvey's approach to dynamical relativity sort of really finds its most natural expression, I think. So here's the sort of technical detail of my proposal. I say individuation structure is given by the action of the group under which all states in the theory transform in the same representation. And by representation, I mean it in the sort of group representation sense, a homomorphism from some group into the set, basically into the group of matrices, which respects the group structure of the original group. These matrices act on vector spaces, which is sort of why everything needed to be linear. And we'll discuss in a while why that's sort of, you're not throwing away too much by restricting to linear states. Linear state spaces, rather. So you find that in most classical linear field theories, that it's the translation group that actually plays this role of defining a group under which all objects in the theory, all states in the theory transform the same representation. Notice it's not something like the Lorentz group or the Poincaré group, because consider something like a spinor field, it's not invariant under a rotation. And so that's not going to qualify as a group under which we want, that's not going to qualify as a group that we're going to use to help structure our space. For those of you some of you in the audience have seen some of the talks I've given earlier. In the context of supersymmetric field theories in superspace, it's the so-called supertranslation group that does exactly this, but that's just an aside. So that's the setup. And what I'm going to try to do now is, in the last 7 or so minutes, try to apply this to a very, very simple canonical non-commutative field theory, and see where we get. So here's something that emergent manifold structure could supervene on. It could supervene on a set. So this is not a manifold of non-commuting events. I don't really know what that might be. Some set of non-commuting events. What does it mean for events to be non-commuting? We'll come to that in a minute. Of course, this is, as we saw when Eleanor presented all of this material, this is part of a more general methodology of kind of identifying different moving parts of a theory and then figuring out a good, consistent way to generalize them. And we find, so when you do the Geroch-style Einstein algebra thing, you discover that all of the dynamical objects that you need to define GR can be defined algebraically. And moreover, they can continue to be defined algebraically even when you remove this requirement of commutation. So what's interesting about these sorts of canonical non-commutative field theories, and by canonical non-commutative field theories, I just mean field theories in which the non-commutation of these events is proportional to some antisymmetric theta type factor. Whereas Eleanor was interested in trying to see whether or not there was some physical significance to those thetas, and she came to the conclusion that they couldn't be on grounds that they didn't transform in any sort of physically reasonable way. I argue that the thetas actually just encode something much simpler. They're just a shorthand for encoding the fact that we don't have a manifold description of these events all the way down. It encodes the deviation from this classical notion of events going all the way down to the manifold. And the way that they do this is by appeal to an appropriately defined multiplication operation given by the Moyle star. Now, I assume we don't really remember, well, I certainly wouldn't remember the general form of the Moyle star. I didn't put it on my slides because it takes really, really long to write it up in LaTeX. So I'm just going to write it just schematically over here. So if I've got two fields.
Can you use the black pen, please?
Sure. Yeah. So this is the Moyle star.
You can take the poster off.
I'll put it back on. Okay. I'm just going to write this out schematically. It's a bunch of I's and a bunch of J's. And right, so basically what the Moyle star encodes is the deviation from sort of the ordinary sort of pointwise multiplication in the real numbers that we're used to. And we have a second, and again, this is a bit of an abuse of notation. We have a second expression that involves the Moyle star, and that's in terms of anti-commuting coordinates. I forget if it's a plus or a minus, but it tells you about how under this kind of operation, two space-time events fail to commute. But the interesting thing is, I mean, this is an operator acting on fields. It's just the same symbol, but this doesn't really encode anything other than a really simple way to talk about how eventually to get to this multiplication operation, which is to say, really the Moyle star is defined on the algebra of fields, and there's some equivalent kind of shorthand that we can define on the arguments that these fields take in order to ensure that this dynamically privileged Moyle operation goes through. Incidentally, again, just to come back to some things that I've said in other talks, this is not necessarily, this is not the case in superspace geometry, where we also have a bunch of things that look like they're formally put into the theory just to ensure manifest covariance under the super Poincare group. In that case, I argue that those actually have some kind of physical salience. But in this case, it's not true. And the reason that it's not true is because of the very definition of the Moyle star. Whatever it is that the Moyle star does can be expressed as some cumbersome sum of ordinary multiplication, which means we can always, at least to the extent that we want to think about fields as being functions of some kind of events, we can always think of them as being functions of events on some kind of commuting manifold. But just as Eleanor said, a commuting manifold whose geometry doesn't respect the geometry that the dynamics would find the most natural. So notice that in my prescription earlier, I spoke about the transformation behavior of states, not the transformation behavior of the dynamical laws. Now, the states that we define in these theories, these phi of x and psi of x type things, will presumably continue to be the same kinds of fields that we defined in our commutative theory. They'll be things like scalars or vectors or spinors or whatever. And they will continue to transform trivially under the translation group defined on that state space. Now remember, for event individuation, we weren't so much interested in the dynamics, except insofar as the dynamics had an impact on the property of these states. And so whatever the dynamics, the coordinates, given that we can assign these kinds of coordinates to these fields, the structured space associated with these fields, with the transformation behavior of these fields, is characterized by a local invariance under translation. And this structures our Kleinian structured space, what I refer to as spacetime, as a local affine space. Of course, given that we're dealing with a flat space theory, this is just an affine space. And of course, an affine space has a topology. We get a lot more than we had asked for, which is nice. But all we had asked for was that we'd be able to structure our space as a Hausdorff topological space, and that's what we've got. We've managed to individuate events, and so that's basically all I had to say. We can use this notion of spacetime having something fundamentally to do with event individuation to argue that certain symmetry properties of the fields that make up, the dynamical fields that make up our theory, will govern how it is that we measure sort of physics associated with those fields. So I'm just going to conclude really quickly because I think I've just come to the end of my half hour. So I started off by trying to ask what a sort of a minimal characterization of spacetime might be in order for the theory to be empirically coherent, in order for a physical theory to be empirically coherent. I showed that, well, I didn't show, but I proposed that you don't need necessarily fundamental local variables. All you need is sort of emergent event individuating structure. And this event individuation was what I thought of as being an important aspect of spacetime, and this is what mediates the connection between some putative theory of quantum gravity or something like a non-commutative field theory and it's being empirically coherent. Now, I've called this algebraic functionalism, algebraic because it applies to these sorts of theories that are not necessarily easily interpreted as being geometrical. Functionalism, insofar as its function was just to identify a structure that individuated events. We then looked at an example, just a really simple example of a linear canonical non-commutative field theory in which the states are translation invariant. That structured our structured space with a whole bunch of structure, and among all of the structure that we got was Hausdorff topology. And then just as a final note, the claim that a non-linear, non-perturbative quantum theory of gravity admits a space-time description will not be affected by the argument that I just gave today, because my entire argument depends on representations, and representations, at least in the way that I've defined them, can only be applied to linear spaces. I'm sure there are plenty of people in this room who are going to sort of choke me for saying that, but anyway. But I still think that's okay. This accounts for a very, 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 very large class of theories that we think of as being sort of serious physical theories. And if it turns out that we want a space-time description in sort of non-perturbative quantum field theories, well, I contend that you'd need some further justification for why that might be the case. Now, it might be the case that we were able to probe that empirically, and then sort of we would require a space-time story to be told at sort of whatever level we probe. In that case, this is out the window, and we need to come up with something else. But if it's just that, we like space-time and we'd like space-time to continue sort of as far down as possible, well, I think it requires sort of slightly more than that. And I think with that, I've just run out of time, so I'll stop. So thank you.
Okay, and comments by John Doherty from University of Illinois Chicago as visited, but I think we should also say University of California San Diego more permanently.
I think he might be out of UIC by now.
I think I've got 2 or 3 minutes.
Maybe the end of the month.
Yeah.
Okay.
Cool. Thanks. So I really enjoyed your talk and have a lot of questions, but I'm going to restrict myself to 3.
Okay.
So the first one's sort of clarificatory.
Yeah.
I sent you these beforehand, so but I'm going to still pretend.
I was going to pretend I was coming up with the answers off the top of my head. Thanks for that, John.
Sorry. Okay, so you started out by talking about the easy problem and the hard problem of space-time,
Yeah.
and then so you're going to talk about the easy problem. The way you stated originally is that if the metric is, the second way you stated it was if the metric's quantized, how do we individuate space-time events, following the Geroch quote. So on the next slide, you said that individuation is done by the topology, not the metric. So in light of that, the easy problem, as stated before, it doesn't really make sense. The metric seems irrelevant to individuation, so whether or not it's quantized doesn't really have any bearing on that issue. So later, you then, I guess, ask how the metric acts as an event individuation field, and answer that it's really the topology that does it. So I'm confused about what the easy problem is supposed to be at the end of the day, what you're taking yourself to be answering. If it's to do with the metric, it seems well posed, and if it's to do with the topology, it seems well posed, but not what you're talking about. So it's true that in some quantum gravity programs we do lose topological structure, but they don't seem to be like the ones to which this approach is going to apply, right? They're like the ones you're talking about at the end here. Cool. So, do you want me to just do them all?
Yeah, okay.
Okay, so 2. So moving on to your program, I have 2 worries. The first has to do with the setup, and the second with the application. So, despite the question that I just asked, it doesn't seem to me that topology plays any individuating role. So it seems like topology is usually used to represent closeness, either spatiotemporal or conceptual or something like that. I'd have thought that facts about identity or individuation are represented by the set that you started out with, that M on slide 11. So if that's true, then it seems like you just stipulated the individuation facts at the start, and I don't see what the Kleinian point of view is getting out of it for you. So then the second worry has to do with moving on to the actual approach with the criteria in your offering. So as I understand it, algebraic functionalism, the idea is that we're going to pick out the structures that are properly called spatiotemporal by appealing to a certain universal character of space-time. So something like this seems like a good idea to me, but I'm not sure I understand exactly the details here. You say that the spatiotemporal structure is associated with a group, and that this group is picked out by the fact that all states of the theory transform in the same representation of that group. But I don't know how to make sense of this criterion in a way that doesn't presuppose that we already have the structure you're looking to get out. So how are we going to decide if 2 representations are the same? If we have 2 fields and representations of the translation group on the state spaces of each, then these representations have different spaces, so we don't have a way of comparing them to ask whether they're the same or different. If we're thinking of these fields as assignments of values to manifold points, then we have a way around this problem, because then we can use the sort of natural representation of the isomorphism group of the underlying space, and just say that 2 representations are the same if they factor through that in the same way. But the specific goal here is to avoid talking about those points to compare these things, so that doesn't seem like an option for you. So how are we supposed to compare representations?
Great, thanks, John. So off the top of my head, so let's do the let's just go through this in order. You're right. So let me go back to where I posed the. Where did I pose it? Yeah. Yeah, you're right. So thanks for pointing this out. This actually I think this is just a bit of sort of presentational sloppiness. Basically, what I've said is, so kind of sort of implicit in this is that the metric, the metric insofar as it's a tensor, will agree on this event individuation, the space-time event individuation structure with whatever it is that the topology on that space is. So really, yeah. So this problem sort of splits into two, and I feel like you're right. I've spoken about one aspect of it. So if it turns out that the space-time metric is to be quantized, that doesn't necessarily mean that the quantization procedure is going to do anything to the topology, to the underlying topology. But it seems like when you look at stuff like the Geroch quote, you kind of assume that they're in the ride together, and so it seems like the quantization process will upset the this sort of topological individuation structure just as much as it upsets this metric sort of length and distance structure. So all I was trying to do in setting up the easy problem of quantum spacetime in this case was to show that those two things are not necessarily the same. Again, okay, so maybe we can come back to this if you're not satisfied with that. So the second question you asked was, it seems like I'll just paraphrase. It seems like what I'm saying is, look, I've got these events already in some set, and now I just want to talk about how they're individuated. But hey, presto, I've already individuated them because I've just told you I've got a bag of events. And that's true, except that I might have this bag of events, but until I define some kind of, until I figure out some way of dynamically probing whatever it is that I might associate with this bag of events, I have no way of individuating them. So yes, it might turn out that they have primitive individuation structure, but what I claim is that the dynamically informed, the transformation of fields informed Kleinian geometry associated with them gives me a topology, and specifically gives me a Hausdorff topology that allows me, if not to individuate every single event in that bag, to individuate regions of that sort of disjoint open regions of that bag that will correspond to the sorts of sort of disjoint events that I see on my emergent space-time manifold. So that was sort of what I had in mind over there. The final question was about comparing representations. Yeah, thanks for that question. That kept me up all night. Not really. It was. So yeah, I mean, in a sense, it's what I mean to do is I want to say something like, look, we have a fairly robust notion of what it is to transform in, say, the scalar representation or the vector representation. And what we mean when we say things like that is, look, I've got some state space of my fields, not even necessarily fields, whatever, so my objects. And I might have sort of 2 isolated systems, I might have 3 isolated systems, I might have a description such that I'm able to incorporate all of them into a single state space. But I still have a way of talking about the representation of some symmetry group as acting on the state space of, okay, let me just name these things. So I've got 3 fields, forget 3, I've got 2 fields, phi and psi. And let's say they're both spinor fields. For whatever reason, I've told you that they're both spinor fields. I can talk about them. Well, part of what's definitional of the fact that they're both spinor fields is that I can, on their individual state spaces, define representations of the spin half representations of the spin group. And that's the sort of really minimal way in which I'm talking about sort of representations being the same across state spaces. So another way of putting this might be, so the reason I had the universality thing was this is a remnant from the broader discussion in the context of superspace. But in this particular case, when we're dealing quite unequivocally with groups as opposed to supergroups, we could also frame this as the group under which all fields or all objects transform in a one-dimensional scalar representation, a real one-dimensional scalar representation. And that's sort of the sense in which I mean it's the same across the fields. So that's...
Okay, time for questions. Or I miss. Oh, you have a question. I thought you said that. Okay, sorry. Al.
Cheers. So I was hoping to hear sort of more about how the algebraic functionalism relates to the kind of functionalism that Eleanor was describing. So you talked about event individuation. She was talking about inertial frames. And I wondered how those were connected, whether one of those roles kind of subsumes the other, or whether they're both kind of, you think of those as kind of independent features of the space-time role?
So I think in theory they're distinct, because I could, much like, based on the question that John had, where sort of topology and metric, at least the algebraic function of the metric split, it might be the case that I have a theory in which the event individuation is given by these sort of Hausdorff topological conditions, and then the metric structure just doesn't respect that. So if I were to look purely at the metric, I wouldn't be able to sort of individuate events in the same way. I might still be able to, but I wouldn't be able to do it in the same way. It just so happens that in the theories that we're interested in things like GR and special relativity, whatever, the metric and the topology, the metric and the metrical and topological notions of event individuation sort of line up perfectly. But what I wanted to do was sort of prize them apart and just leave open the possibility that there was going to be a scenario in which these two things didn't happen. And I wanted to, maybe the slightly stronger version of the claim that I want to make is I want to privilege the topological, like what the topology says about event individuation above what the metric might say.
So thank you. I'm not quite sure that I understood in the end exactly what how the application filled out altogether. So part of this would be to just maybe say that again. But let me say a couple of things about bits of the argument that I kind of heard along the way. And two things sort of struck me. You put these two things on the board here, and it sounded a bit as if you were saying they were different things. But of course, the bottom thing is just what the first thing says in that particular, when the fields are X and Y, right? So they're not really like different in that sense. And I think it's right that it's also, if you think of X and Y as generators of the fields, that bottom relation entails the top relation for polynomials in X and Y. So they're not really like two different.
Oh, so I mean, oh yeah, sorry.
Okay, so you agree with that, and so given that, I'd like to hear again exactly what work that the distinction between those two things was doing. But maybe I'll throw the other point in, because I think it's sort of also related. So you said something like, the YL star is just there because the fields, I'm not quite sure how you put it, like respect the dynamics or something. That's the kind of multiplication you're supposed to do in the action. I think it is what you mean.
Yes.
But there's a real kind of tradition in philosophy of space-time. So this, you might say, yeah, that's right, that's what I think, because I might have misunderstood what you were saying. But right, there's a real, you cited Harvey, but it goes back to discussions with all kinds of people that if you don't want more structure, then actually appears in the action. So if the Moyal star multiplication is the right kind of multiplication in the action, then somehow the geometry ought to respect that, maybe.
Yes.
And I sort of heard that you were kind of pushing, it sounded like you were pushing back on that in a way. So maybe it is, I still don't quite understand what an event is in this case.
Okay.
Is it sort of a field with compact support or something like that?
Yes.
I'm just going to say one more thing in case it's sort of relevant, and I should have said it earlier. In applications of this stuff, right, the kind of fields you're generally interested in fact, are polynomials in the coordinates.
Yes.
And sort of more than that, they probably disappear at infinity as well. All right, so there was a couple of kind of technical things there, but I guess the main one was, what work exactly is the distinction doing, and are you giving enough sort of, taking seriously enough the fact that it's Moyal star multiplication in the action? Does that sort of make sense?
Yeah, yeah. Thanks, Mike.
Wasn't coherent.
So the first thing is maybe I didn't put this as well as I ought to. The only sense in which they're different is that it's a star, and in one case it's acting on elements of an algebra on elements of whatever set these objects sit in, and in this case it's acting on elements of some different set. So it's just, as a purely mathematical operation, it's just got different domains and different domains and different targets. So, but what
One's just a subset of the first one.
I mean, if this is, so if I'm thinking of this as a field in the standard, assigning properties to points of space-time kind of way, then this takes a value, and supposing it's a vector field, it'll take a value in, say, R3 or whatever. But this is just something that's going to take a value in some, I mean, it might by coincidence also be a vector space R3, which is the coordinate space, but it might not be. They're objects that sit in different sets, in different spaces.
I think you guys found the space of fields in the Gaussian function.
Yeah. I mean, that's what I'm saying. They're polynomials in X and Y.
Yeah, the closure of the space of polynomials.
But are you thinking them as purely algebraic in the bottom and as file representation fields in the top?
Yes, yeah. I mean, that's. I mean, the point is. I mean, how's it that? I mean, okay. Forget the more.
I mean, X just. I mean, if you think of that as on the manifold in some set of coordinates, I mean, X just is a field that assigns the value of the X coordinate to every point.
Yeah, but it's a different field from the phi of X, which assigns some field value to that point.
No, that's a particular phi of X. The phi of X equals the X field.
Oh, I see your point. Okay. In that case, I don't have a response to what you said right now.
So much so that you can derive the first star product by a definition of the star product at the level of coordinate functions.
I mean, yeah. So that. Yeah. I mean, that seemed to me to be sort of why you would do that. That seemed to be the utility of defining them on. But you're right. I mean, so that was a mistake. I thought of these as being sort of in separate spaces. But the point I was trying to make about this was merely that, fine, modulo sort of slippage about what spaces these things are defined in, that the Moyle star sort of applying these to sort of one, I guess, privileged set of fields, sort of these X and Y fields, the fact that they can be expanded as the fact that these fields that can be expanded as polynomials of this field just tells you that all of the information is basically the same between the two of them, and that's kind of that was really the point. This just seemed like, it seems like you might be tempted then to give some kind of to tell some kind of story about what these X's and Y's are, in terms of sort of some kind of geometric, or I don't want to say pseudo-geometric, but sort of algebrogeometric entities that are in some sense distinct from the phi's. And what I wanted to say was, look, no, that's not what's going on over there. This is just a convenient shorthand for expressing facts about the dynamics, which will concern not just sort of the field, when phi of X is equal to X, but when phi of X is equal to sort of whatever else that field might be. That's sort of what I had in mind over there. But to come to, maybe we can talk about this a bit after.
No, there's two more questions.
Okay, so the second question was about sort of the dynamics of the Moyle star versus the geometry of the Moyle star, as opposed to sort of the kind of geometry that I was trying to talk about in terms of these phi fields.
Well, the question. So, given you have an action where, I mean, just think about. So, I imagine these are scalar fields. So you have a sort of phi-4 theory, but instead of ordinary multiplying of phi, phi-4, it's
phi star, phi, yeah.
satisfies, what implications does that have for the geometry?
I mean,
Is it just a sort of, we just happen to have a fancy, kind of complicated action here, or is it saying something about the underlying geometry?
I mean, I think it's definitely saying something about the underlying geometry. I mean, this is. I think this is the point that you make in your paper as well. It's it looks like it's giving you a representation of fields on. So when you go into the Wilde representation, it looks like there's one geometry which is just the Minkowski geometry, and then there's this other geometry, this sort of weird this geometry that arises from these dynamics. And the question is, well, which is the real geometry? So I'm perfectly happy with the idea that they might not coincide, and I'm sort of, I am given my sort of predilection for agreeing with what Harvey says about these sorts of things. I'm likely to think that the geometry associated with the Moyle star is the one that we ought to take seriously. But what I was, the point of, in some sense, disregarding what it is that the Moyle star was doing, was really to look at the geometry that was associated with sort of transformation properties of the states, that in such a way that it was independent of the geometry, so as to be able to get this the topological sort of event distinctness that I was after from the start. And it might, it might turn out that actually this is I see the point now. It might turn out that even at the level of topology, the distinction there might still be distinct topologies. In which case, again, I'm going to have to think about that.
So Chris, and then it's Julius after that, and we have like 4 minutes. So.
Okay, I tried to be brief. So my question is much more elementary. At the beginning, you seem to introduce algebraic functionalism as the patch which is supposed to help us over any threat of empirical incoherence that we might incur by not having local variables at the fundamental level. But then towards the end, or in the conclusion, you say that algebraic functionalism is the idea that it is the spatial temporal degrees of freedom that individuate events, which are those which play the role of individuating events. Something like that was on one of your last slides.
Yes.
But then so if you have either those spatial temporal degrees of freedom are the fundamental ones, in which case I don't know exactly what the original problem was supposed to be that we're solving, because then if you have spatial temporal degrees of freedom at the fundamental level, in what sense do you not have local variables? If we didn't have, if those degrees of freedom were not the fundamental ones, then just to say that it is the spatial temporal ones, non-fundamental degrees of freedom somehow that then will do the individuating, isn't the solution to the original problem.
So,
do you see my puzzlement?
Not quite. I mean, so if you don't mind repeating it.
So if algebraic functionalism is the idea that it is the spatial temporal degrees of freedom that do the individuating, either those are fundamental or not. If they're fundamental, then
there's no point.
We don't have the original problem. If they are not fundamental, then that position doesn't seem to address the original problem which we now have.
Okay, so here's the thing. So I was, again, this comes back to this conception of sort of the different roles that you might expect sort of space-time to play. And again, sort of in the broader thing of space-time as being a cluster concept. All I wanted to say was, look, you may choose to call these degrees of freedom spatiotemporal or not. You could call them space-time, you could call them space-time prime, whatever. What I'm saying is the structure that you get from the dynamics of the fields that allows for empirical coherence, for the presence of local variables at the level that we're going to be doing experiments, insofar as we sort of take for granted that they're not going to be fundamental, will have to be the result of some kind of some kind of dynamical process or some kind of process associated with things that you can do to these fields.
Yeah, so functionalism is the idea to get
Yeah.
from the fundamental level to that by
Yes.
functionalizing those roles and
Yes.
finding the realizers at the fundamental level.
Yeah, so what I'm saying is,
Where that from?
so at the fundamental, but what we have at the fundamental level is just the fields. We don't have a representation of the fields as
Yeah.
functions from, but the transformation behavior of the fields is what allows you to.
Go ahead.
Oh, good.
So one may think that for classical GR, it kind of doesn't matter whether you go algebraic or metric,
Mhm.
right? Because
Yeah.
they are equivalent kind of numerical
Yeah.
style. And would such equivalence results be unsettling for an algebraic functionalism? It kind of seems like there's, if you excuse this, dark side of the algebraic functionalism. Namely, you're privileging one of the mathematically equivalent formulations, so you better have very good reason to do that.
But I mean, the privileging is only at a sort of methodological level, because so in a case where you've got a perfectly well defined sort of geometric picture as you do in GR or whatever, fine, you might I mean, in that case there is no real problem, because the entire theory is built in such a way to have sort of event individuation in sort of the ground level. And the whole point of this was to give you, it wasn't so much to sort of in any way ontologically privilege sort of an algebraic view of whatever theory. It was just to say, look, if you've got a theory which you may or may not have a geometrical description of, but you do have this algebraic description of, you'll still be able to find something. There's still some way, there's still some algorithm that you can throw at this that will allow you to have this event individuation structure, which is just part of sort of a long Christmas list of things that you might actually want from the theory.
Okay, let's thank Tushar and John again.